Hey everybody, welcome back to Physics 2. We're going to start some new content today. One of my favorites, magnetism. And there's 8 sections in this chapter. We're going to try to hit all of them. We may skip a couple of aspects in one section, but it'll come up in another. I'll be clear about that when we get to it. So the goals for this chapter are to understand how magnetic forces behave, how magnetic fields interact with moving electrons and charges. And then we're going to look at one specific application of magnetic fields and electric fields called a mass spectrometer. And then we're going to look at how current carrying wires interact with magnetic fields. And then we'll introduce a new law, Ampere's law. Very similar to Gauss's law. It's a little bit of a conceptual law, but we're going to do our best to wrap our minds around it. So to review, you may want to revisit uniform circular motion. I will review that when we get to the section that requires it. Simply recall the electric field line properties. Okay, the rest of the stuff, we'll review it when we get to it. So in this first section, it's a lot like the other first sections of every chapter. It's just basically introducing you to the subject. And the idea here is that magnetic forces, well, they have some similarities to electric forces, like the fact that they act on other objects at a distance, but there's also some distinct differences, and we'll talk about that. So magnetic forces act at a distance just like electric force, but they can be much stronger. Okay, they can have a lot stronger force. And you probably have some intuition about that already because you've seen how magnets can snap onto a fridge, right, quite quickly and strongly. You may have even played with some really strong neodymium magnets and saw how strong that they interact with each other, that they attract each other. And so we're going to dive into that more. So magnetic forces and magnetic fields, we use them all the time in technology. For example, Earth generates a magnetic field, and compasses are objects that align with that magnetic field. So there's this needle here is magnetic itself, and it lines up with the magnetic field of Earth. And so we use that to guide us if we were lost in the forest. And in a scrapyard, we can also use magnetic fields to pick up metal and move, messed up, busted up cars around in a scrapyard. So we're going to talk a lot about Earth's magnetic field coming up here. So what I'll just tell you here from this slide is that Earth's core is what generates the magnetic field. And we'll talk about what exactly is in Earth's core and how it generates the magnetic field. So to wrap up, right, magnetic forces can act over large distances just like electric forces, but there's going to be some key differences in the behavior of those forces and fields. So one of the big key differences between magnetic fields and electric fields is that magnetic fields and magnetism in general, they require the charges to be moving. Okay, so when we were studying electric potential, electric field, those charges were always sitting still, right? With magnetism, in order for a magnetic field to be produced, in order for a magnetic force to be felt, that charge needs to be in motion. So that's one of the main key differences between electric fields and magnetic fields. So a similarity. Electric force and magnetic force, they both depend on the distance between the two objects, okay? So the stronger the force, the closer the objects are together, and vice versa. The magnetic force, however, is not another form of the electric force. It's totally different. But they have the attractive and repulsive qualities that the electric force has. So, for example, we have 2 bar magnets, okay? And magnets in general have a north and a south pole. Well, the north and the south pole of the magnet, which are opposite polarity, are attracted to each other in a very similar way that positive and negative charges are attracted to each other. And same polarity, north and north or south and south, they are repulsed, they repel each other. They're not repulsed by each other, but it's funny to say things like that just to help you remember. So that character is very similar, but what you may notice off the bat is that, you know, positive and negative charges, they are just single objects, right? However, a magnet, it kind of has, it's almost like having a positive and negative charge built into it. Except we don't call it positive and negative. We call it a north and a south pole. So a magnet has this dipolar nature built into it. And we'll talk more about that. So we can look at the field lines of a magnetic object, okay, in the same way that we look at the field lines of a charged object. And we can use a bar magnet and some fine iron filings, okay? So this is just ground up iron. Iron is a magnetic material, so it interacts with magnetic fields. And when we sprinkle the iron filings around the magnet, they're going to kind of rotate and align with the magnetic field, and that helps you see the magnetic field. And so magnetic field lines, there's a special rule, just like we had a rule for electric field lines. Magnetic field lines always leave the North Pole. Let me use a different color here. Right? They go out of the North Pole and into the South Pole. So if you want to think of an analogy here, you could think of as the North Pole being the positive and the South Pole being the negative, okay? As far as relating it back to electric field lines. So magnetic field lines, they always leave a North Pole and go into a South Pole. So these are the poles of the magnet, right? These are kind of like positive charge and negative charge, except they're both located on one magnet. We use the symbol B to represent the magnetic field, okay? So B represents the magnetic field, whereas E represented the electric field. So let's take a look at the Earth. It's a little bit, it can be a little bit confusing because when you think of pole, you might think of North and South Pole, which are geographic locations on the Earth, right? The South Pole is where Antarctica is, and the North Pole is where the Arctic is. But in a magnet, we have poles as well, and these are magnetic poles. So we have a magnetic north and a magnetic south. And so the way that the field lines point in Earth is that they come out of the South Pole and go into the North Pole, right? Geographically. But remember how we had those field lines in the previous slide? I'm going to draw them right here. We had a North Pole and a South Pole, right? The magnetic field lines come out of the north and go into the south. So when we're talking about Earth's magnetic field, we need to make sure that we are speaking about the magnetic pole and not necessarily the geographic pole, okay? So the geographic North Pole, right, where the Arctic Circle is, all right, where northern Canada and Russia are, Siberia, near the north of our Earth, that is actually the magnetic South Pole. I did not realize that this is actually incorrect. This is the magnetic South Pole. Right? Because why? The magnetic field lines are entering that area. And actually, so let me just make this correction real quick. I don't know if you've heard in the news, but the poles of Earth, the magnetic poles of Earth, actually reverse every, I don't know, 50,000 years or so. We have some evidence and rocks that show us that the poles reverse from time to time. They also slightly move their location. So like the strongest field lines in the north, geographic north, may be located here, and over time they kind of move around. Well, they actually also flip. So pretty soon this figure will be correct. There is evidence that the poles may flip sometime soon. So it's pretty crazy stuff. Look into it, Google it if you're interested. So one of these days, this figure may be correct, okay? So it's pretty neat stuff. And we're going to talk about what is actually inside of the Earth that's creating the field. But I want to wait to talk about that when we start talking about how moving charges are related to magnetic fields. But for now, we're just kind of getting used to the character of magnetic fields, right? So North Pole, magnetic field lines leave the North Pole and enter the South Pole. And that's a magnetic pole, not a geographic pole. So we call magnets dipoles, right? Dipoles, because they have two poles that are built in, right? We saw an electric dipole where we had a positive and a negative charge separated by some distance d, but all magnets are dipoles because embedded inside is that dipolar nature. So you will never find a magnet that is only a north or a south pole. So let's talk about that attractive and repulsive force between the poles. So opposites attract, okay? Same as electric. Same character or behavior as electric particles, electric charges. Okay, opposites attract like repel. Okay, same character as electric charges, but they are not like electric charges. So the way that they are not like electric charges is that this dipolar nature is built into the magnet. So no matter how many times you shrink or cut in half the magnet, it will spontaneously produce a bipolar nature. That is the character of any magnetic object. You cannot ever separate the north and south pole. So if you have a magnetic material, if you have a magnetic object, it always has this dipolar character built into it. So here's another interesting observation, right? So these are all observations, and that's how we start our physics, is we're just looking at, characterizing our observations. What do we see about the Earth? Well, it produces a magnetic field. What are these field lines that come out of a bar magnet, right? We're making a bunch of observations now, and then we'll get into the math and take a look at the math that helps us explain the observation. So here's another observation. If you run current through a coil shape, so instead of running current through a straight wire, let's say that you curl that wire like this, okay? You loop it around. So like you place a pencil in there and then you curl the wire around. Well, what happens when you run a current through there is that it produces a magnetic field in the center of the coil, okay? So another observation is that current, moving charges, right, can create magnetic fields as well. So this, some of these slides are a little bit wordy, and I kind of say what's on the future slide, before we get to it. So if I'm skipping a couple of slides, it's because I've already mentioned or talked about what the text on that slide. So let's kind of like understand the nature of this coil that has a field Okay, let's say we don't know anything about this field. We don't know if it points this way or if it points this way, right? So let's see if we can figure that out. So if we bring a bar magnet close to the coil, well, first let's define the current direction just so that we have a basis, right? We're gonna send the current in this way, okay? And then it leaves that way. So we send in the current that way and we bring a bar magnet close. And what we see is that when the south pole is facing that coil, that they're gonna attract, okay? So that means that this is kind of like the north pole of the magnet, okay? If we were to represent the coil as a magnet. And if we were to send the current in the other way, then we would see that the magnet would repel. So again, sending in the current changes the polarity of the magnetic field coming out of the coil. So then the north pole is going to move over here, and then the south pole would be over here, right? Because they feel a repulsive force. And so if we replace that magnet with another coil and send the current in the same direction for both, then we're going to get an attractive force, right? Because this would be the north pole, right, on the side that the current's leaving. And then this would be the south pole, which is the side that the current is going in. Okay, right? See, current going in south, current going in south. So, in other words, these coils behave like a magnet. And therefore, this coil passing a current through it produces a magnetic field. Okay, that is the conclusion that we're coming to here by looking at these examples, right? We are proving to ourselves that a coil actually produces a current flowing through the coil, right? There must be a current flowing through it. Current through the coil produces a magnetic field, and therefore current, moving charges, must produce a magnetic field as well. So keeping track of everything that we've talked about, right? Not only do magnetic objects like a bar magnet, a piece of iron, a neodymium magnet, not only do these rocks essentially create magnetic fields, but moving charges via a current creates a magnetic field as well. Okay, so it's pretty amazing. So does magnetism always involve charges in motion? And the question is yes, right? But if we're looking at a piece of iron, where's the charges in motion there, right? If we're looking at a magnetic rock that we, picked up while hiking, where are the moving charges in that material, okay? Well, moving charges exist in all of us, actually. If we are made of atoms, we have moving charges in our bodies. And that's because the outside of the atom, there's many ways to look at the electrons on the outside of an atom. You can look at them as the shell model, as the cloud model, right, with the orbitals, the orbital model, many different ways. And all of those models tell us that electrons are constantly circulating and rotating and moving around an atom. And so they then, since they are a moving charge, essentially they're little currents, and they must be producing a magnetic field. And the atomic structure of magnetic objects like iron, nickel, cobalt, right? These are all elements that are magnetic inherently. It has to do with the electron structure outside the atom and why that structure creates a magnetic field. But we all have moving charges. If we're made of atoms, we are also made of moving charges because of the electrons outside the atom constantly moving, okay? So they're not really two different things, right? If we're talking about a magnetic piece of iron or a coil with a current flowing through it, they're not two different things. They're essentially the same thing, but just in two different applications, right? Here, it's the electrons in the cloud, in the atomic, structure. structure moving around, creating the magnetic field. And here it's a current carrying wire, which are electrons moving, creating a magnetic field. So it's essentially they're both creating a magnetic field because of moving charges. So let's take a look at this conceptual question, okay, where we compare the behavior of electric and magnetic forces. So let's say we have two identical objects and they both have positive charge Q. One of the objects is held still and the other one is in motion. Okay, so the other one is moving around. What kinds of forces do the objects exert on each other? Is it both electric fields and magnetic fields, or forces, that is? Just electric, just magnetic, none, or depends? So we have one still and one moving. So let's look at the case of the still. And this one's moving. So let's look at the case of the still charge. What forces are acting on it? Well, there's definitely the electric force from the other charge, right? Which is going to be a repulsive force. So we're going to have an electric force here. And what about a contribution from the moving charge? So we know that moving charges produce we know that moving charges produce magnetic fields. But does a still charge feel a magnetic field? And the answer is no. So there is no, the charge that is not moving does not feel a magnetic field. We know that moving charges produce magnetic fields and thus a force, but the charge needs to be moving in order to feel the force as well. So charges need to be in motion in order to feel a magnetic force. Okay? So the still charge does not feel a magnetic force due to the moving charge. And so what about the moving charge? I mean, obviously we can answer our question, but let's just finish the kind of thought experiment. So this charge is moving. What forces are acting on it? Well, it definitely feels the electric field from the first Q, right? Which is repulsive. It feels the force due to that electric field. Is the still charge producing a magnetic field? No. So therefore the moving charge is not going to feel a magnetic field from the still one because it's not moving. So charges need to be in motion to feel a magnetic force, and then charges need to be in motion to produce an electric field. Okay, and so therefore B is our answer, right? They feel electric forces due to each other, but they don't feel magnetic forces because the still charge is not moving, so it won't feel the magnetic field produced by the moving charge. And B, the moving charge doesn't feel a magnetic force from the still charge because it needs to be moving in order to produce a field. Sorry, that's my Roomba in the background. I'm gonna send him out of here. Okay, Roomba has been taken care of. So this section was all about just making observations about magnetic fields, okay? We saw that magnetism is an interaction that only occurs between moving particles, okay? A moving charge creates a field, and a moving charge feels a field, okay? Still charges do not create fields, magnetic fields, and still charges cannot feel magnetic fields. And magnets basically have charges in motion, right? those charges are the electrons circling the atomic nucleus. So not only do current carrying wires produce magnetic fields, but certain materials can produce magnetic fields because of the special arrangement of their atoms and the electrons that move around those atoms. So now we're going to get quantitative, okay? We're going to look at the force, the magnitude of the force, and the direction of the force that a moving charge feels, okay? So we're going to begin our study by considering one charged particle that's moving in a magnetic field, all right? So we have a charged particle, and there is already a magnetic field existing, created by something else. All right, so in the same way that we looked at Q and how the forces of Q act in an electric field, we're looking at the forces that act on a moving charged particle Q in an already existing magnetic field. So to summarize some experimental observations about charged particles moving in a magnetic field. Number one, when a charged particle is moving in a magnetic field, it feels a magnetic force, but that's only when the charged particle is moving. We already know that. And number two, the magnetic force depends on the direction of the particle's velocity. Okay, so there is a directional dependence. So the velocity direction of the particle is going to affect how strong the magnetic force is, okay? So in relation to the direction of the magnetic field. So that was the same as electric force, right? We saw that F equals QE, and if Q was negative or positive, right, it changed the direction of the force. But now for magnetic fields, we don't know how it's related, but the velocity, I guess, is what is going to change the sign of the force, okay? So there's some relationship here. The magnitude, number three, the magnitude of the force is proportional to the charge. All right, that's the same as electric force. So there's definitely a Q in there somewhere. The direction of the force is perpendicular to both the direction of motion and the charged particle. So there is, there's going to be some directions associated with, and that's that little dot with the circle is a vector pointing out the page, right? There's going to be some kind of direction for each one that we need to be concerned about. So it's a little bit more complicated than electric fields, right? And then finally, the fifth observation is that the sign of the charge also changes the direction of the force, very similar to electric fields. So let's summarize all of those points into an equation, and this equation is what does that, okay? The force that a moving charged particle feels in a magnetic field is equal to the sign of the charge times the velocity of the charge, the magnetic field that it's in, and then sine of the angle between V and B, okay? So this is giving us the magnitude of the force. So that means that this is a magnitude, right? This is the magnitude of the particle's charge. This is a magnitude of the velocity, and this is a magnitude of the B field. So these are all going to be positive values that we plug in, okay? And what's going to give us a negative sign, if there is one, is going to be this guy right here, the angle between the magnetic field and the velocity. So that is the equation for the force that a moving charged particle experiences when it's in a magnetic field. What about the direction, right? This is magnitude here of that vector, the force vector. What about the direction of the force vector? Well, we're going to use something called the right-hand rule, that's the abbreviation, to tell us the direction of the magnetic force. And the way you do that is you point your fingers in the direction of V, and then you curl them into B, and the direction that your thumb must point in order to do that is going to be the direction of F. So I take my fingers and I point them in the direction of the velocity vector, and in order to curl them into B as they are in this picture, my thumb would have to be pointing up, and this is all with the right hand. Here's a mathematical way to think about this, okay, if your brain works like that. Think of the plane created by the velocity vector and the magnetic field vector, right? So if I were to create a plane, which is, I take these vectors and make a square out of them, right? And this is a sheet of paper lying flat on the table, then the force vector is perpendicular to that sheet of paper. In other words, if the velocity vector is on the x-axis and the magnetic field vector is on the y-axis, right, then the sheet of paper is in the xy plane. The force vector is perpendicular to that, and the force vector would be in the z direction, okay? So these directions are all perpendicular to each other. So that's the right-hand rule. This describes in text how to do the right-hand rule. We can watch some videos, and there'll be some videos posted of how to use the right-hand rule. And so what happens then, how does the sign of the charge affect the right-hand rule and the direction of the force? Well, for positive charges, you can use your right hand. And for negative charges, you still use your right hand, but then you flip the direction, okay? So after you do the right-hand rule, if you notice that that charge is negative, the direction of the force is flipped from your thumb. You can also, fun fact, use the left-hand rule. So if you use your left hand to figure out the direction of the force, you don't have to flip anything. The thumb on your left hand will point in the direction of the force. So this is kind of explaining that kind of what I did before, right? In certain cases, if V and B are perfectly perpendicular, then the force direction will be perfectly perpendicular to the plane created by V and B. But V and B do not have to be perfectly perpendicular. V and B can be, close together or far apart, but the plane that they create is always going to be perpendicular to the force vector, okay? What is the SI unit of magnetic fields? It is the Tesla. The Tesla is a unit that is shorthand for a bunch of other SI units. For example, a Newton second over a coulometer, or a Newton over amp meter. So it's a very complicated unit. That's why we just shorthand it for Tesla. The strongest magnetic field that any person would experience occurs actually in an MRI machine, where 2 Tesla magnetic field is kind of shot at you, right? And that's in order to measure the parts of your body that have very, weak magnetic fields due to electrical impulses, like blood circulation, right? Blood has iron in it. So not only is iron magnetic, but it's moving, right, through your blood vessels, right? So it's a moving charge as well. And the MRI machine helps pick up those signals in your body and give you a nice contrast so we can kind of see, the outline of organs or bones. So there's another unit for magnetic field, and that is the Gauss. So 1 Gauss is 10 to the minus 4 Tesla. Okay, so Tesla is a very big unit, and Gauss is used when, we don't want to be talking about microtesla and picotesla and tiny little units. We want to kind of have a better, gauge of the size of the magnetic field. So be aware that there are two units for magnetic field, the Gauss and the Tesla. And so in this cautionary slide, this watch out slide, we're going to just take a look at the difference between the force due to an electric field and the force due to a magnetic field. So the force due to an electric field, we know it's QE, right? The force due to an electric field is always parallel or anti-parallel to the electric field. However, the force due to a magnetic field is never in the same direction as B. It's always perpendicular to B. So for magnetic fields, the force that a moving charge feels is always perpendicular to B. That is one of the most distinct differences between electric fields and magnetic fields. So let's look at some ways that we represent 3D vectors on a 2D PowerPoint or a 2D piece of paper. And we do that using a circle with a dot or a circle with an X. So the circle with a dot is a vector pointing out of the page at us. So imagine this little dot as the tip of the arrow coming out at you. Okay? And if the vector is pointing into the page, this is going to be the tail of the arrow, right? And the old school arrows, they have the little tip and then there's feathers at the end. So you can think of the X as looking at the feathers, head on. All right, let's do an example, okay? Magnetic forces on a proton and magnetic forces on an electron. All right, in this example, we're somewhere near the Earth's equator, and the magnetic field is horizontal, meaning it's parallel to the ground and pointing north. So to kind of show you what we're talking about here, right? Here's Earth. And remember we saw that the field lines, they technically go into the geographic North Pole, right? And they come out of the geographic South Pole. But this is the magnetic north, right? And this is the magnetic south. So that's why the field lines point into the geographic North Pole and out of the... So anyway, if you're right here near the Earth's equator, and I were to draw another one of these field lines kind of going straight up, right? In order to do that, that magnetic field vector points up, right, towards our north. So that's the setup of this problem. We're right here somewhere, and parallel to the ground. So, right, this is kind of like a top-down view if we're right here. So if I'm standing on the ground at the equator, the north direction is going to be into the page. Does that make sense? Right? I'm standing up, my head, you can see the top of my head right here. And if I'm looking from this direction, the north direction is going to be into the page. Does that make sense? Think about that. If that is like weird, think about it. Think about looking at Google Maps, right? You're looking down at a map and north is pointing up. But if you are in Google Street View, depending on where you're looking, north could be behind you, right? And that's where we are right now. North is pointing that way. So and it's parallel to the ground, right? Because the ground is here and the vector is going in and out of the page like this. Well, you can't really see how my hand is pointing, so it's parallel to the ground. The magnitude of that field is 2.5 times 10 to the minus 5 Tesla. The question is, what's the direction and magnitude of the magnetic force on the particle if the particle is moving at 1 times 10 to the 4 meters per second? Okay, and then we're given different directions and different charges. So let's tackle that. So another way we can write this, if this viewpoint was confusing, that's totally okay. I just wanted to bring, because you might get problems where you need to kind of look at this in 3D, okay? If that's difficult for you, you can always turn a 3D problem into a 2D problem. And so let's do that. So in a 2D problem, if I'm drawing, let's go back to map view, right? Not street view, but map view. Here's our geographic locations, north, east, south, west. And then the magnetic field is going to be pointing due north. So our magnetic field direction is this way. Okay? There's a 2D view. So part A, we're dealing with a proton. So we have a positive charge and it's moving. So the charge is plus E, right? That's the charge of a proton, which is 1.602 times 10 to the minus 19 coulombs. And that proton is moving horizontally due east. Okay, so that means it's moving somewhere in the northeast southwest plane, due east. So if I just copy my little picture here, put it right next to this, part A, the proton is moving this way. Okay. That's the velocity direction. And the question is, what is the direction and magnitude of the magnetic force? So the magnetic force magnitude we saw is given as QVB sine theta. So Q is 1.602 times 10 to the minus 19 coulombs, right? And these are all positive values that we plug in here. The velocity given to us is 1 times 10 to the 4 meters per second. Magnetic field, 2.5 times 10 to the minus 5 Tesla. Now, what about the angle between V and B, right? This is the angle between V and B, and that is 90 degrees. So sine of 90, that's 1. So our answer is basically for the magnitude, all those numbers multiplied together. So let's do that. Okay, I got 4.005 times 10 to the minus 28. And what are the units of force? They're newtons. All right, tiny little force. Tiny little force. What's the direction of the force? We use our right-hand rule because we're dealing with a positive charge. Fingers in the direction of V. Curl them into B or sweep them into B. And my thumb is going to be pointing out of the page. So the direction is up or out of the page, right? Out of the map, right? If this is a map, if this piece of paper is a map, it's pointing straight up out of the map. So now what about an electron moving in the same direction okay? So now this electron is moving in the same direction, part B. Well, what changes here? Does the magnitude of the force change? No, because we put in positives for everything anyway. So the force is the same. But the direction changes. We can use the right-hand rule and flip our sign of the force. And so that would mean the force would be pointing into the page. Or if we use our left-hand rule, in order to sweep V into B, you're going to see you have to rotate your hand so that your thumb is pointing down. So you can use your left-hand rule to sweep V into B, and you'll see that the direction is pointing down. Or into the page. Two ways you can characterize that. Part C, a proton moving horizontally in a direction that is 25 degrees east of north. All right, east of north. So now our proton, I want to move that black thing. Oh well, I guess it's there. Right, so our proton is moving east of north. So east of north is here, okay? And 25 degrees east of north is this angle. So now our angle between V and B is going to change. So now when we find the magnitude, we're going to have our 1.602 times 10 to the minus 19, our velocity, which is 1 times 10 to the 4. Oh, you know what? I think I just realized I wrote the velocity wrong in my calculator, right? I wrote 10 to the minus 4. It should be 10 to the plus 4. And so this becomes 10 to the minus 20. Sorry about that. You're probably in the video like, hey, hold on. When is she going to realize this? I realized it now. Okay, sorry about that. I just plugged in minus 4 instead of plus 4. And when I wrote this down, I just realized that. So times the magnetic field, 2.5 times 10 to the minus 5 Tesla. I dropped my units. Let's write them back. Now, now sine of what angle? The angle between B and V. And that is going to be exactly the angle that was given to us this time. Okay, in your homework, it may not be. So you need to be careful, right? Make sure that the angle you're plugging in is the angle between the velocity and the magnetic field. So now when we plug that in, times sine of 35 or 25. And our magnitude goes down to 1.69 times 10 to the minus 20 newtons. Okay, but what about the direction? The direction is still straight up, right? Because I'm sweeping the velocity with my fingers into the magnetic field and my direction is still pointing straight up. That did not change, even though V and B are not perfectly 90 degrees from each other, right? It doesn't matter. The direction of the force is going to be perpendicular to the plane created by the velocity vector and the magnetic field vector, and it doesn't matter if they are 1 degree apart or 359 degrees apart, right? They still create a plane that's like a sheet of paper, and the magnetic force will be perpendicular to that sheet of paper. Kind of like the area vector is perpendicular to an area, right? When we did flux, the same relationship. And instead, now that area is being traced out by the velocity vector in the B field. So the direction is still straight up, okay? So that's how we're using and finding the magnetic force. We're still breaking up that vector into magnitude and direction. So let's move on to this got the concept question, okay? Questions like this will appear on exam 2. So try your best to understand it now so that when you're studying later, you're not starting from scratch, all right? So we have a proton. We're looking at this proton here. And it's fired into a region of a uniform magnetic field that's pointing into the page. That's why the little purple X's are there. And the proton's initial velocity is shown by the blue arrow, the blue vector. What direction does the proton's trajectory bend? Okay. So if the trajectory is starting off as going to the right, when that proton starts feeling a magnetic field, so when it gets in here, it's going to start feeling a force on it, pushing it in a certain direction. And that's going to change its velocity vector, right? Because now there's a force acting on it, making it go not straight. So let's figure out what direction it's going to go. So the velocity vector is to the right, and the magnetic field is pointing into the page. Okay, this is kind of a 3D picture, right? You have to imagine a vector arrow pointing into the page. And what you want to do is you want to imagine that vector kind of being tail to tail with this guy. So imagine it being right here, okay? Pointing into the page. You take your fingers in the velocity direction and you're going to curl them into the page. And your thumb, in order to do that, your thumb is going to point straight up. Your thumb is going to point straight up, right? And so those are 3 perpendicular directions. So that checks the boxes, right? That makes sense. So V is to the right, F is up, and B is into the page. So if you want, you know, we can kind of, let's draw a 3D axis, right? Let's call, I don't know how you like to draw it. I like to do X, Y, let's see. Let me draw it a different way, because I have to make sure that my X and crossing my Y is going to be pointing up. So X, Y, Z, right? This is like a corner of a box here. So my B vector is going to be represented by, that's not the greatest explanation, is it? So my F vector is pointing straight up. And so every time this proton moves with his velocity V, he's going to be pushed up. And so what direction then is his trajectory bending, right? Every time he moves, there's going to be a little force on him, pushing him up, little force on him, pushing him up. And so he's going to start bending towards the top of the figure, right? He's going to start bending towards the top of the figure. So ask yourself this question for all the electrons in this picture as your preparation for exams. Check directions for electrons. And I think in some of the, we're going to actually be doing that in some of these other got the concepts too. But the way that the question, they're going to ask the question a little bit differently. So now let's do another one, right? So now let's look at the electrons. And we're given, again, red arrows to show us the direction of their initial trajectory. So these are all of their velocity vectors. And the question is, which electron could the trajectory lead to a point on the left-hand side where the proton enters the region? So in other words, where could the electron end up right here? Okay, not anywhere here. It's kind of confusing the way it's worded. What the question is asking for is where could any of these electrons, or which, I guess, let me rephrase that, which electron would land right there where the proton enters? Okay, which one has the potential to do that? So let's look at electron A and do the right-hand rule. So velocity is pointing down. The B field is into the page. So I'm going to take my fingers, point them in the velocity direction, and curl them up towards, or I should say curl them into the page towards the B field. And then my fingers are curling like into the page, and my thumb of my right hand is pointing to the right. But since we're dealing with an electron, so what I'll do is I'll draw this. So, right, the force of the proton would be to the left, which means the force of the electron would be to the right. So the force direction, did I say right? I meant to the left, okay? The force of the proton is to the right, but since we're dealing with an electron, we have to flip that direction, and the force of the electron is pointing to the left. You could use your left hand, and when you do that, you're finding you're going to have to rotate your left hand so that your thumb is pointing to the left in order to sweep V into B. So for proton A, the force on this particle is going to be constantly pushing it to the left. So every time he moves, he's going to be a little bit more to the left. Every time he moves, he's going to be a little bit more to the left. So he does potentially have the trajectory to hit this proton where it's entering. So electron A is a possibility. What about electron B? So electron B, let's do our right-hand rule. Let's draw our vectors, right? So the velocity vector for electron B is pointing to the left. So this is B. The magnetic field is pointing into the page. We're going to let's use our left hand. Okay, I'm going to have to rotate my hand in order to be able to get my fingers to point in the velocity direction and sweep them into the page. And that's going to make the thumb of my left hand pointing up. So this is going to be the force on the electron, pointing up. So this electron is going to be curving up, and therefore it will not hit proton where the proton is entering the field, okay? So it cannot be B. What about electron C? Electron C is going to curve the same way as electron B, right? And depending on how fast the velocity is, how strong the magnetic field is, or how weak, it does have the potential to hit where the proton enters. So electron C is also a possibility, right? Remember the force of that arrow pointing up and pushing that electron up? Well, that is equal to QVB sine of the angle, right? But depending on the strength of these three characters here, the charge, the velocity, or the magnetic field, that's going to affect how strong that little force arrow is and how strong that curvature could be or how weak that curvature could be, okay? So that's the idea here and why electron C could possibly hit the proton's location. What about electron D? So we use our left hand to point our fingers up in the direction of the velocity. The magnetic field is into the page. So I'm going to take those fingers of my left hand. I'm looking at the back of my hand. I'm going to sweep them into the magnetic field, which is pointing into the page. And I'm going to see that the thumb of my left hand is pointing to the right. So the force on that electron is pointing to the right, and then it's never going to hit, it's never going to hit that proton. Okay? So electron A and electron C have the potential to reach this point right here where the proton enters the field. And that's what we have right here. Okay, so this question is tricky because it's not asking, which electron could hit this side, right? It's asking which electron could hit right here. And that's A and C. So in summary for this section, we looked quantitatively at the magnitude of the force that a moving charge feels when it's in a magnetic field. And we also looked at the direction of that force. And the direction of that force is perpendicular to both V and B, okay? The magnitude was proportional to the charge, the speed, and the magnetic field magnitude. And the unit of magnetic field is Tesla or Gauss. Okay? Now let's look at an application of these forces on moving charged particles, and that application is a mass spectrometer. And what a mass spectrometer does is it uses forces to kind of differentiate between atoms of different masses. And so let's see if we can figure out how that works. A mass spectrometer is basically used to identify molecules and atoms. And the first thing you need to do to start this process is you need to take your sample and you need to put it into what's called a velocity selector. And you put your sample in there, and what that does is your sample being these little protons here, okay? So we're going to be, pretending our sample is just made of positive charges for right now to understand how it works. So we put in our sample, it's a bunch of positive charges. We put them in the velocity selector, and what the velocity selector does is it applies an electric field in one direction and a magnetic field in another direction. Okay, and those directions are perpendicular to each other. So when a charged particle that's moving with a velocity v is in the presence of both an electric field and a magnetic field, it's going to feel two forces. It's going to feel a force due to the magnetic field and a force due to the electric field. And so what are the directions of those forces? Well, the force due to the electric field is going to point to the left. Why is that? Because the E field points to the left and the charge is positive. The force due to the magnetic field is going to point to the right. And why is that? Because the velocity vector is up and the B field is out of the page. So we use our right hand to point our fingers in the direction of the velocity arrow. And you're going to have to flip your hand in order to curl them out of the page. And you're going to see that your thumb of your right hand is pointing to the right. So we have a force acting on the particle pointing to the left, which is the electric force. And then we have a force on the particle pointing to the right, which is the magnetic force. And if those forces equal each other, that particle is not going to feel a net force in that direction, right? It's going to go straight. If those forces were uneven, and let's say that the electric field was bigger, well, then that particle would start moving that way. And if the magnetic force was bigger, then that particle would start moving that way. So only particles that feel equal amounts of force due to both the electric field and the magnetic field will go straight into the actual machine, okay? So you do this first because you want to kind of like eliminate some particles that you don't want to measure. And you want your sample to be as refined as possible. And so you want to eliminate certain charges that don't fit this, right? That don't have these balanced forces on them, and send them away in a way, maybe going this way, maybe going that way. And only the ones that you want to measure are going to go straight. And so let's see what are the ones, which particles fit that criteria. Let's figure that out. So if those magnitudes of the forces are equal, what are those magnitudes of the forces? Well, F electric is QE, right? F magnetic is QVB. Angle between V and B is 90, so it just becomes QVB. And if we set those equal to each other, and we solve for velocity, because the Q's cancel, what we see is that only particles that are moving with a particular velocity will go through to the mass spectrometer. And that's why it's called a velocity selector, right? So we are refining the particles based on their speed. And so only particles with a certain speed will enter the mass spectrometer. And that's because we're going to send a certain electric field, we're going to send a certain magnetic field, and only the ones that balance the forces will go straight. And those will be the ones that enter our mass spectrometer. So we haven't even, we're still describing kind of before we start measuring, right? Before we start measuring the sample, we're refining our sample and allowing only particles with a certain velocity to enter the mass spectrometer. And so now, when they enter the mass spectrometer, what happens? So now they've made it in. Great, they're in. What happens now? Now we apply only a magnetic field, okay? And that magnetic field is, again, out of the page. And so if the velocity is pointing up, and the particle has a positive charge, and the B field is pointing out of the page, we take our right hand, fingers up. You got to flip your hand over to look at the palm of your hand in order to curl those fingers out of the page. And the force direction is to the right. And that's why you see this curvature here, right? The particle, as it comes in here, is going to feel this force vector to the right, curving it. And you're going to get a tight curvature for a low mass ion. And you're going to get a wide curvature for a higher mass ion. And so let's take a look at the math that tells us that, okay? How do we know which way it's going to turn? How do we know how tight the curvature is and how wide the curvature is? Well, that's where the uniform circular motion from chapter 5 comes in. So it follows a circular path. We can use Newton's second law to find the radius of the curvature. Okay, so this particle is moving in a circular motion, okay, because of that force always being pointing to the right, And when an object moves in circular motion, we know that its acceleration is always equal to v squared over r. So if we start with F equals ma, we know what this force is on the left. This is the magnetic force. We know this acceleration on the right. This is acceleration due to uniform circular motion. This guy right here. We can plug those both in. It looks like my equations didn't show up here, but that's just fine because we can do that. We can write it ourselves, right? What's the magnetic force? It was QVB, mass, times the acceleration of circular motion, v squared over r, equal sign. And then we can solve for the radius of this path, and we can see how it's dependent on mass. So if I solve for r, I get mv squared over qvb, and I get a v that goes away, and I get that my radius is proportional to mass. So as my mass increases, my radius increases, and vice versa. As the velocity changes, right, the velocity increases as well or decreases the radius. And then Q, so if the charge of my unknown sample decreases, then I have an opposite or inverse proportionality, right? So you can get all sorts of clues now from the radius of curvature. And does it go this way or does it go this way, right? Positive charges will go this way. Negative charges would go the other way if we were to get them through here, but we would have to flip this stuff. So, but you get the general idea. Okay, we're just gonna talk about it with positive charges. So you can see how the radius of curvature ties in with the mass. It's proportional. And that's what a mass spectrometer does, right? So we have all these unknown mass positively charged particles, and we're going to be able to see the little splatter marks of where they hit. And we're going to be like, oh, we have a bunch of low mass particles and no medium mass particles and a bunch of high mass particles, okay? And so that's how a mass spectrometer works. So you count how many ions land at each location, and you can see how your sample is composed. Is it composed of, really low and really high, or is it composed of maybe all one, right? Maybe they're all very close to each other. You have a pure sample. So that's the idea of a mass spectrometer.